Alright, so today we're going to start out looking at examples of representations. So example 1. We're going to let G be a Lie algebra over K, and of course M is going to be a G module. So here that the G module structure on M and the trivial structure, the trivial G module structure on K define a G module structure on the K module of N, which is the module of bilinear forms on M. So two inputs, both from M, and we sent them to K. Then we have that the action of X and N on some beta, some function beta in N, on two elements M and M prime is equal to negative beta of xm acting on the first element with the second plus, and the positive is, that should be M prime, sorry, not X prime, is M X M dot M prime. So for a given beta in N, given by linear function on M into K, the set of X in G such that the action of N on B turns into the zero map is a subalgebra of G. Now, continuing on, let M be a K module with a bilinear form beta on M as above, and from the above the set of X in the general linear Lie algebra of M, or the endomorphisms of M, such that beta of X on M and an M prime in our second argument plus x acting on the second element equals 0 for all m and m prime in our module is likewise, as we can see, a Lie subalgebra of the general linear Lie algebra of M. Now, suppose K is a field. Field M is finite dimensional, as always. And that beta is non-degenerate. So then every x in GL of M admits a left adjoint x star relative to beta, which is everywhere defined and the subalgebra from above is the set. I always try to write that as one word for some reason. General linear Lie algebra elements X such that their adjoint, left adjoint, is just negative X. So you see here, when X switches over, switches size in beta, it turns the whole thing negative. Is the idea there. So by this process, we will be constructing some. First example, we're going to take M to be k to the n, and our bilinear form beta acting on C and eta. And it returns the, you multiply them component-wise and then add up each term. And so we canonically identify GL of k to the n with the matrices of k to the n, the n-dimensional n by n matrices of k, I should say. Then the Lie algebra we get is the Lie algebra of skew-symmetric matrices. And we note that when our base field K is the reals, this is the orthogonal Lie algebra, which, if we recall from the very first episode, this is the tangent space of the orthogonal group as a vector space at the identity matrix. So that's our first example. And we've got a second one. So these two both seem important based on what they're setting up, sorry. Now, in the second example, we're going to take M to be a bunch of K's before, but this time we guarantee that the dimension is even. So it's 2 times M, and our bilinear form is this xi and eta I. I guess we'll index it with j just to be clear. This is equal to the sum of I from 1 to M of xi times eta M plus I minus eta I xi M plus I. Kind of a confusing bilinear form, but I will trust it. And so the matrix of beta with respect to the canonical basis, with respect to K2M through its canonical basis, is, so beta equals, so has 0, the m dimensional identity, the inverse of the m dimensional identity, and the 0. Now we're gonna let, why is this lagging all of a sudden? We're gonna let U be equal to a 4 by 4 matrix, which we write as 4 m by m matrices. And this is, of course, with respect to the canonical basis of K2M. This is the matrix of an element U in G, general linear Lie algebra of M. And then set then U star has the matrix 0, so this is negative beta, or equivalently I'm thinking the transpose of beta, times the transpose of u times our regular old identity and this gives us back a matrix that looks like this. That is a B in the top corner. I just drew it bad, as I'm drawing everything bad. So thus, having this u star equals negative u is equivalent to the set of conditions that D is the negative transpose of A and B and C are their own transposes. They're symmetric, I believe, is the term. And as before, you get a special condition when K is the reals. Oh, I should mention before, this is the real orthogonal Lie algebra. And here the algebra when case R is the real symplectic Lie algebra. Alright. And so these are two subcases of our first example. And we have a second shorter example with the same setup, as in like the same letters all mean everything. So here, the G module structure on M defines on the K module, so just an ordinary module of what we're saying is P, which is linear maps of K linear maps of M on itself. This is also, I believe it's saying that this is the endomorphisms of M. And this is, of course, defining a G module structure. Then for all x in G and U in P, we have seen that x, the P action of x on U is equal to the bracket of mx with U, which is equal to the composition, or is equal to the adjoint of x and M on U. So in other words, x in P is equal to the adjoint representation of x in M in the linear maps of M comma M, which is L of the general linear Lie algebra of M. Alright, so that was our first part of today. Let's go on to our second. I believe we gotta verify how long this is gonna be. Yep, this should be the right length. The other topic, which we should hopefully cover in full, is invariant elements. Definition: let G be a Lie algebra, M a G module, then an element M in the set M is called invariant. If everything in X and everything in G sends M to 0. Keep in mind, once again, the Lie algebra is kind of like the set of speeds, derivatives of the corresponding group. So the corresponding idea in the group, I believe, is going to be, this is like the equivalent of the derivative of a map being 0, I believe. Kind of. Don't take my word on that, but that's what I'm thinking here. Oh, they go through it here. Once again, I did not read enough far ahead before talking, so this is going to be a bit ahead. They put notes here if text is a bit ahead, and this one is, so I usually skip these, but let's get into this. Let G be a connected Lie group, connected real Lie group with Lie algebra G theta, an analytic representation of G on a finite dimensional real vector space E with corresponding representation rho of G on E. I'm going to let M be an E. Then M is invariant with respect to rho if and only if theta g on m equals m, what I was saying. It is no speed, essentially, for all g in G. And this is why it's called invariant, because the kind of map that this is the derivative of is constant, so this is 0, loosely. Now let's look at an example. Let m and n be G modules and P be L k-linear maps from m to n. For f and p to be invariant, I guess we'll say that f of p is invariant if and only if that f is a homomorphism of the G module M into the G module N. In particular, I will specify here it is a G module homomorphism. If M equals N, I specify here that xm is xn, so they're the same set with the same structure. F is invariant if f composed with xm equals xm composed with f for all x in G. Alright, we've got 3 examples. Here's our second one. Let M be a K module with finite basis. If M has a G module structure, then I saw before the linear map of M into M and the tensor product of the dual space of M with M have a G module structure, and the canonical mapping of M star tensor M into L of M is a G module isomorphism. Now as 1, the map 1 in the linear map of M into M is obviously an invariant. The corresponding U in M star tensor M, I believe. So one is the map sending everything to the identity, I believe. And so it's invariant because by the bracket, I believe it's going to get sent to 0, no matter what is bracketing it. So the corresponding U in M star tensor M is also an invariant if EI from 1 to N is a basis of M, with a dual basis EI star, then U is the sum of all EI stars tensor EI. And we have one last example before we move on to a couple propositions. Going to let M be a G module with a bilinear form beta and beta has a corresponding F in the linear maps from M to M star. Now, beta is invariant if and only if F is a G module homomorphism Now suppose K is a field and that the K dimension of M is finite. A non-degenerate invariant bilinear form on M defines an isomorphism of M tensor M as a G module onto M star tensor M as a G module. Thus, by the previous example, beta defines canonically an invariant element C in M tensor M as a G module, as we wrote. And what is C? Let EI be a basis of M and we're going to let EI prime a basis of M such that beta of EI and EJ prime is 1 if they match, and if the indices match, and 0 if they don't. Then C is just the sum of EI tensor EI prime. Alright. Here's a proposition. Let M be a semi-simple G module then the submodule M naught, M0 of invariant elements of M admits a unique supplement stable under these XM namely M1, which is generated by the XM dot M for X in our group, our algebra, sorry, and M in our module. And how do we know this? Well, I did these in the wrong order anyway, so. And let M prime and M be a submodule stable under the XM and a supplement of M naught in M. And for all M and M, M is equal, M splits into an element of M naught and an element of our M prime, which is our supplement. and hence x sub m acting on m, well, the 0 term is invariant and so it disappears, and so this is just m prime in m prime. Hence, every element in m1 is in this m prime. Now, let's m2 be a submodule of m prime stable under the xm and supplementary to m1 in m prime. Then for all m and m2, x to the m acting on m is in m2 intersection m1, which, since there's a supplementary, is just 0. This holds for all x and g. Hence m is in m0, so m is 0. Hence m2 is 0, so m1 is m prime. Now, one last proposition to end things off, which I actually was supposed to show before, and I did not. Let G be a Lie algebra not just a Lie algebra, a Lie K algebra. So Lie algebra of K is an ideal H. A representation rho of G on M with rho prime being the restriction of rho to H. Then the set N and M of elements in M, of course, invariant with respect to rho prime, is stable under rho of G. Let's look at the proof. We're going to pick an element N in this N and Y in this G. Then for all X and H, since it's an ideal, bracket of X and Y is an H, which gives us that rho X, rho Y of N is the bracket of row xy of n plus row y, row x and n, row x of n, since everything is stable, x is in H, this is an H, this is an H, and so the actions both are going to be 0 by invariance. Hence, row y of n is in n, as desired. Yeah, and we still got a ways to go here. Another 2 or 3 videos on this. Might spend all of like what's actually tomorrow. I know for some reason I always use the word tomorrow to refer to the next video, but we'll probably spend all of actual tomorrow on finishing up representations, and then hopefully we'll be done and we can move on to our next topic. So look forward to that.